This is G484 homework booklet question 21. So to start with, state in terms of force the conditions necessary for an object to move in a circular path at a constant speed. What I need for that is for the resultant force to be perpendicular to the velocity, that is towards the centre. Quite explicitly, don't get any marks for talking about the centripetal force. If you like, the centripetal force is a term we apply to the net force, to the resultant force, once we've established that it is always perpendicular to the velocity. But if you're looking to see if something is doing circular path, you can't talk about the centripetal force because that's assuming we've got the situation we're being asked about. Of course, the key thing here is because the force is, well, it's two things. Circular path, the perpendicular force can do the change of direction to keep it going in that circular, keep changing direction to give us a circular path rather than going in a straight line by Newton's first law. But also because it's perpendicular to the direction, it's doing no work, therefore it's not transferring any energy, therefore we get that constant speed that is talked about there. Explain why the object is accelerating and state the direction of the acceleration. Obviously it's not changing speed, so at a most simplistic level it might appear not to be accelerating, but the velocity is changing. Why? Because the direction is changing. So the velocity of the direction is changing, and state the direction. Well, F equals ma is a vector equation, so if the force is towards the centre of the circle, then that must be where the acceleration is, so the acceleration is towards the centre. Part B is not a straightforward question. It's not a question we've necessarily done before, although you do obviously know everything you need to do it. The satellite moves in a circular orbit at that constant speed, and we've got the mass of the Earth being that. You're asked to calculate the radius of the orbit. Now, I've not given you an equation relating radius to speed, but we do know that whenever we're doing orbits, what we're talking about essentially is that the gravitational force, gmm upon r squared, is providing us with the centripetal acceleration, is the centripetal force mv squared upon r. So if I equate those two, I can very quickly see that the little m's, the mass of the satellite in this case, cancel out. Multiply it by r squared, divide by v squared, and I end up with this equation here. R is gm over v squared. Lob the numbers in, and I get a radius of the orbit, 2.92 times 10 to the 7 meters. But the key to that question is having the confidence to say, well, I don't really know what's going on, but what I do know is that the force, the centripetal force, is provided by gravity, so let me equate those two things and do what I need to do. Of course, what you're most used to seeing is sort of getting to this stage and then putting in that v is 2 pi r upon t to get the equation that relates ultimately t squared to r cubed, but that we didn't need to do that here, so we just needed to have that confidence to shove those two equations together and see where it took us. And in fact, it fairly straightforwardly took us through to the answer. In order to move the satellite in B to a new smaller orbit at decelerating force, how can we do that? It's hard, of course, to put forces on things in space because there's nothing to push against. So what you have to do is to fire something forwards. If you want to slow down, you've got to fire something forwards. You put a force on it to accelerate it forwards. By Newton's third law, it puts a force on you to accelerate you backwards. So what you have to do in some sense is to eject some mass forwards, in other words, in the direction of travel. In practice, that means firing a rocket for a small rocket forward, and so as you give that rocket fuel forward momentum, it will impart a backward force upon you. And then finally, the radius of the new orbit is that side, as we're asked to calculate the speed of the satellite in this orbit. Again, we're being asked to relate velocity and radius. The point is I've already done that, so I simply returned to here, picked up that equation, r is gm upon v squared. I'm after a v this time, so I've just multiplied by v squared divided by r and got v squared is gm over r, lobbed in the numbers, 4,500 meters per second. But really the work for that one was sorted out back when I was doing part B. So that's G484 homework booklet question 21.